Right, Jeff? And you are now the presenter.
Thank you. Thanks everyone for joining today. My name is Jeff Chris. I'm a technical solutions architect, and I'll be joined by Jeff Metcalf, who's a technical marketing leader in the business group that has been developing the X-Series. So with that, let's just jump into it. So this is the agenda for this morning's session. You'll see we're going to go over some of the hardware details, the chassis, and then we'll go through the components. And the way it's laid out is you will get an overview, and as we go further into this session, there'll be more and more details shared. So you'll get a taste, a high-level view of the components and how they interact to each other, and then we're going to drill down on the components themselves. So if you don't get any of the detail, or we don't get as deep as you think early on in the session, just hang on, because it's probably coming as we drill down into the individual component sections. So with that, let's jump in. So first off, let's start with where we're at. And you can see the architecture here. It is similar. It's not just similar. It is the same physical topology, the same fabric that we've had. And we typically don't call it a fabric with UCS, but you can see here we've got our fabric interconnects. And with X-Series, that's the fourth generation fabric interconnects, your 6454s and your 64108s. You know, you've got the same, that is the exact same hardware. So the first 16 ports are unified ports. They support fiber channel, and then you have your Ethernet ports, your 10, 25 gig ports, and then your 4100 gig uplink. So the same as what we've had in the past. What I'll introduce to you as maybe being newer is the intelligent fabric modules, the 9108-25Gs. You know, very, very similar to the IOM modules that we have in our 5108 chassis. And then if you go down a little further, you can see the new chassis. It's the X9508. What I'll share with you is this architecture. You know, we're staying with it. It has very strong bones. It's still very applicable today. It's 11 years old, been on the market for 11 years, but it's still very strong. There's no weaknesses in this, so we're expanding on that. The only real difference you see today is we're taking the policy part, which is the UCS manager, and we're running it in Intersite. So we just call this, Intersite managed. And it's really just taking the policy and control out of the fabric interconnects and putting it at a higher level. A lot of benefits to that, and I'll drill down into it. But this architecture is still valid. It still works today. And so we're going to take advantage of the success we've had with UCS and that architecture and expand upon it with the X-Series. We're going to support up to 20 chassis at first customer ship, which is, just right around the corner. It's going to be 10 chassis and 80 nodes, but that'll expand. So very similar to how when we introduced UCS the first time, we'll just keep expanding that capacity until we hit the 20 chassis, 160 nodes. But you can see the details on the chassis here, and we'll get into a lot of detail around that. So let's just start diving into the system. So the X9508, it's a 7RU, so it's 1U taller than the 5108 chassis that we have today. It is future-proofed, and you'll see optical ready and liquid cooling ready. We'll touch in some detail on that as we go through, but that's really future-proofing the architecture. You'll see quite a bit of change on the power and cooling. So we've got 6 2800 watt power supplies versus the 4 2500 we have in our current chassis, and a 54 watt power distribution versus a 54 volt power distribution versus the 12 volt that we had. We'll go into some details on why we've done that. You'll also see that our fans have been increased in size, so you can move the same amount of air at a lower fan speed. It's all around efficiency when we're talking about power and cooling. Using more of that power for what the customer is buying. That's the actual compute functions. Now, for the intelligent fabric modules, we'll go into detail on those. There are 2 in each one of the chassis, and there's also 2 X fabric modules. And this is really in the future. There's not real processing in these X fabrics today. The fabrics are there to provide some cooling for the back of the chassis currently, but that's really future-proofing technology that has not existed until today, and that's post first customer ship of these devices. So this is the chassis. It's it's somewhat revolutionary. It's wide open. There is no real mid-plane in this. In this form, the chassis is a little over 90 pounds, so there's not a lot there in this configuration. Fully loaded, the chassis with nodes will somewhere between 400 and 450 pounds. So the weight is in the compute nodes themselves. And really, why we designed this way is to prevent technology lock-in. When speeds and feeds to the backplane change, we can simply change out the fabric modules and a VIC card, and you can take advantage of those speeds and feeds or the technology that will be offered. With removing everything from the chassis like this, we've reduced airflow restriction, so it breathes easier. We've also increased the voltage from 12 to 54, and that's really about maximizing efficiency. So, when the components can take advantage of the higher voltage, you get more power for the same amount of amps that you have to put into the system. And really, it's just flexibility. And you can see here, it's you can mix and match nodes as those become available. You can see the power supplies laid out in the front, and I'll point out the orientation of the blades as they slide into this chassis is the top part is actually facing to the left. So all the blades as they slide in, the top will be to the left. We'll have more details on that as well. So this is where it is different with the vertical orientation of the nodes. The nodes themselves slide down the rails, and in the back, they connect to the IFM, the Intelligent Fabric Modules. And you will have 2 Intelligent Fabric Modules in each chassis, and each of the VICs, as we'll go into the detail later, have dual connections to both of those fabrics. But the node itself slides down the rails, and you'll feel the insertion and then the seating as you latch the node into its slot. At that point, it's energized. It'll has power to the blade itself, and it'll have dual connections to the top and bottom IFM at that point. That in effect eliminates the midplane. And you can see in the pictures in the lower right where the fans are oriented in the back of the chassis. They're oriented in the middle, and they obviously pull air through the chassis itself. Now the X fabric is at the bottom of the chassis, and its connections are very much like the IFMs at the top. There will be dual fabrics offered, And this is really, more of future looking at shipment, at ship. There is no real X fabric being delivered in the chassis. So all of our network traffic, IO, goes out of those top IFMs, not the FFM. So the XFM, the X fabric is at the bottom and the IFM at the top. So that is where all the IO will take place in the 9508, is through the top IFMs. So we do have Cisco VIX, and this is based off of the 1400 series VIX that we have in our M6s today. So very much like those, based off the same ASIC. And what I will point out here as you look at this, it's a modular LAN motherboard. It contains the two connections to the intelligent fabric. So if you look at the orientation of this, you see the two physical ports. Through these two physical ports is how we connect to both of the IFMs. This is where all the IO and all the traffic traverses the chassis. This is different than in the 5108s in our previous blade architectures, where the modular LAN motherboard set on the blade itself, and the blade made the connection into the chassis and into those traces. In the X series, all IO will traverse through the VIC. So your system itself, your node, is independent from the VIC, and that connection is made into the intelligent fabric module. So all IO traverses out of the node through the VIC into the IFM, like as opposed to today, you have the modular LAN motherboard, but that traffic goes back through the blade itself to get to the IOM modules. So this is the pathway for all IO to leave. That has implications because with this, we just need to match up the speeds and the protocols and the timing between the VICs and the IFM, independent of the node, the compute node that's in the system. So we could change up VICs and IFM with no changes needed for the node, the compute node itself. So those two things are independent. A quick view of the chart of the differences between the 5108. I mentioned already the difference in the size. It still has the same number of slots within the chassis itself. So we have 8 nodes versus 8 blades in the 5108 chassis. The big difference I'll call out, you can see there's considerably more power available in the 9508, and that's a function of the 6 2800 watt power supplies. So considerably more power, because we're going to, and as you see later, the workloads that we're going to be running with this chassis can take advantage of the newer CPUs and GPUs that are coming to market that require, that ask for more power. The 54 volt distribution just means that for the same amount of work or power that we want to be distributed within the environment, the chassis means we can do it at a higher voltage, lower amperage, which means the traces can be smaller. That reduces the the heat that we actually put through the chassis that isn't doing work. There are 4 100 millimeter fans. These have a lot of instrumentation on them. They can vary their speed. We'll go into detail on that. Each one of the fabric modules, whether it's intelligent fabric module or the X series, has 3 fans on it. We'll go through the detail on that. So there could be a total of 12 fans within the chassis, somewhere around 1,000 or above cubic feet per minute. So not quite twice the amount of airflow through this chassis compared to the original 5108. So not only more power, but considerably more cooling in this environment. So we can pull a lot of air through this chassis. Really, when we talk about the network fabric, it's considerably more bandwidth that's going through this system. So wouldn't focus so much on the individual links, other than to point out there is a lot more throughput that we can get on that. And then the X fabric in the future, that's really PCI Gen 4 lanes being lit up across the chassis. That's post FCS. So we're going to table that for a different session. We're going to talk about what's here today. And this is really why we're, one of the reasons why we're future-proofing the chassis. And it's, we know that today, air cool is kind of hitting its limits in the 5108. And even with the 9508, with, nearly twice as much as airflow and more power, we're going to be able to support workloads as they come to market, and as Intel and as the GP and AMD and as the GPU manufacturers come to market with higher wattage CPUs, we can support those. So is liquid cooling something customers need today? Quite likely not. Will all the customers need it in the future? It's likely no, that's not the case. But there are going to be those that likely will need to take advantage of this somewhere in the future. We've had the existing chassis for 11, almost 12 years. We fully expect a long lifespan for this chassis. So this is really about future-proofing the environment to take advantage of that. There is no liquid cooling in the chassis today. What we're saying here is that we future-proof it. We've had rooms, we have room in the chassis. We know how to plumb it out to take advantage of liquid cooling in the future. I know we call it out here water, but it's actually liquid. And we'll be offering this in two different solutions. One is a closed loop liquid solution where the cooling actually takes place within the chassis itself. So nothing really leaves the chassis, it's self-contained. And then the open loop, which really means we're going to use the facilities in the data center at the customer location, where they provide that actual cooling radiator type function away from the nodes themselves. So that's where we just take the cooling and use that coolant within the chassis, but the actual infrastructure to provide that is outside. So this isn't here today. This is really about future-proofing that. And the reason we're doing that is we do want our customers to, buy these chassis and use them for years. And if the workload requires the use of liquid cooling, we want to be able to say yes to that and be able to provide that within the same architecture that we're still using, but the options of either a closed or open loop cooling solution. So that's really about future proofing again, and that's just part of the architecture that's there when these workloads hit the market, CPUs and GPUs. We'll be able to respond to that with these solutions. So let's talk about the fabric components in some detail. So I'll only spend just a few minutes on the 6400 fabric interconnects, because these have been in the market for several years now. There's nothing about these that are different when we connect them to the X-Series. Matter of fact, you can see where I call out here, it supports the X-Series components. That's the 9108-25G, that's Intelligent Fabric Module. It supports the two VICs that can reside on the X-Series compute node, and we'll go into detail on those. Again, they're based off the 1400 series VICs that we have today. X-Series is supported at 4.2. I'll just call out that's not been released yet because the devices aren't actually shipping, but that will be posted when the devices do ship. You can see the different speeds. So 110, 25, those are what's supported today. And those are really the network connections. Those are northbound. And from a fiber channels perspective, you can see it's 8, 16, and 32. The other thing I'll call out is when we connect to the intelligent fabric modules, those are 25 gig connections. And I'll call that out again when we get to those. But again, to the chassis, it's 25 gig connections. So we need to make sure that we have the right optics in there as well. And this is X-Series is only managed through Intersight. So when I talked about that policy being moved to Intersight, that's Intersight managed mode. So the fabric interconnects boot up. You have the choice now between using traditional UCS manager, which runs on the fabric interconnects, or using Intersight managed, where the devices connect to Intersight itself, and you do the management and the policy creation within Intersight. And that is for X-Series only. Now, we can connect traditional 5108 chassis and M5s and M6s into this environment as well. There's not any issues with that. So X-Series in traditional 5108s and M5s and M6s can reside in this environment and commingle without any issue. Now, you cannot take a M6 blade and use that as an X-Series node. Those two things aren't interchangeable, but certainly 5108s and 9508s connected in the same environment or fully supported. There's no issue with that. They'll just be running under Intersight mode. So that was the fabric interconnects, and they connect into the intelligent fabric modules. So some detail on those. So you can see you have 8 ports on the back of each intelligent fabric module. There are 2 of them. So you have a total of 8 to fabric A and 8 to fabric B, and that's the 8 times 25 gig links. The port in the middle is not used. That's just that was for engineering. So there's no connectivity through that port. So you have 8 ports that connect up. You have 32 25 gig ports that connect inbound to the chassis, to the nodes with themselves. So you'll have 8 nodes divided by 32. You got 4 25 gig from each fabric. So each node through each fabric will get 100 gig of throughput. So you can get up to 200 gig per node with 2 fabrics. So a single fabric supports 100 gig. The throughput of the IFM itself is 2 terabytes. So there's no blocking on the fabric module itself. And again, I'll call out the external ports. There are 3 internal fans. The fans do snap in and out. They do require if you have to replace one in the field, you would just pull out the intelligent fabric module and replace it. The fabric modules are hot swappable themselves, so you can pull out the IFM, replace a fan, and put it back in. There should be no loss of traffic or connectivity whatsoever when you do that. So the IFMs are hot swappable, but obviously the fans are not, because you have to remove the IFM itself. And again, this is kind of a summation of what I had just described. It's really talking about the fabric module itself. And we'll go into some detail now around the compute options. So if you look at the X-Series compute node, it is an M6, and the first thing I'll call out is this is the same M6 that we're running in the 5108, the traditional UCS. It uses the same CPUs, uses the same memory. So those things are common. one thing I will call out is the heat sink itself is considerably larger. So, there is more dissipation of heat through that heat sink. So it's a factor of we have more real estate in this node than we have in our M6 blades today. So you do have, more room to do that. It supports the 3rd generation Xeon CPUs from Intel. These are the CPUs that are shipping in the M6, the B200 M6. So those are the ones that are here as well. I've already called out that the VIC, you can get up to 2 VICs on the 210. Each VIC provides a total of 100 gig, and that's 2 by 25 gig to each IFM. I'll go into detail on that. And you get the same thing with the additional VIC if it's added. So you actually get 50 gig per IFM, so 100 gig with 1 VIC, and with 2 VICs, you would get a total of 200 gig through this node. So a couple more things to call out. It is the same memory that we have in the B200. We have the same memory rules for persistent memory using the Intel Optane memory. One thing that is different is you have considerably more drives. You have 6 drives. These drives are, the drive carriers are the same as we've used in our M5 and M6 rack mounts. So those would be interchangeable with this, the drive carriers themselves. Now, not every drive that we've had in our rack mounts is supported in the 210. It's actually a subset. These are obviously going to be considerably newer, but the drive carriers themselves are interchangeable. You've got 6. You'll have an option of 2 different of a controller and a pass-through module or a blanking slot. I'll have more details on that. I'll also call out that the M.2 module resides between the CPUs, and there's no SD card in this system. So if you do need that local type storage, the M.2 is the way to go. It's been the way to go for some time now, especially since we've offered a hardware grade option. And with this M.2, you do have a RAID 1 that will support 1 volume across that. Here's a comparison of the M6. So it's very much the same device outside of the front drives. It's very much the same. I'll also call out, even though the VIC numbering is different, it's other than the throughput that we're getting, the technology is very much the same, but you can see there is considerably more throughput on this system. So here's a schematic, and I'll go through it with some details because there are some things that I want to call out as being different. Number 12 is where I'll start, and that's the modular LAN motherboard that does reside. And here on this drawing, what you're seeing is the blade, the orientation would be 12 is actually the top of the server as you slide it in. So you would take it and slide it in. So 12 is actually at the top and where you would have the connections into the IFM. 10 is where a secondary MAS, the second VIC would go. And 11 is a new component, and that's a bridge card between the expansion MAS or the second VIC to the MLOM. And all it does is provide traces, passive traces from that additional VIC into the across the top of the MLOM so that we can access those 2 connections to the IFM. Remember earlier when I referenced all traffic goes out the VIC into the IFM. So this just bridges the traffic across the node itself so that it can get to those physical connections that head into the intelligent fabric module. So that is different. I'll call that out again in some detail. Obviously, another thing that's different is we have a front MES for drives that doesn't exist in our blades today. So when we look at our nodes, we have more real estate. So we do have a drive MES for this node, for these nodes, and we'll talk about that in some detail as well. So this is the front orientation of the node itself. Again, I've already called out the commonality between these drive carriers and the M5 and M6 C-Series rack mounts. One thing that is different is the OcuLink, and that's item number 13. It's down at the very bottom of the blade and also depicted off to the right. So this is a different form factor for a console port. This is an option to order. We're not going to ship one with every node. So if you do need those, you do need to include those. And what this does is it comes out, and from there it will connect into a traditional keyboard, video, and mouse plug. So it's really about saving on the real estate. You don't have a lot of, real estate's pretty important on these nodes. So we're using the OcuLink, which just comes out and then provides that connectivity into the spider cable with the keyboard, video, and mouse plugs at the end of it. So other than that, this is pretty straightforward as to what you have on the front of the node itself. So again, memory rules, these will be the same across any of the M6 platforms. It's really we're supporting 8 memory channels. So what the sweet spot is going to be 8 or 16 DIMMs per CPU, or 16 or 32 across a 2 CPU system. There is only a slight, and slight being just a few percentage points difference in the bandwidth between using 16 or 32 or dropping back and using 12 or 24 DIMMs across both CPUs. So those are the sweet spots for memory configurations of any M6. No mixing and matching of RDIMMs and LDIMMs. I think we should know that. You can see the memory rules here. And I would refer you back to the M6 memory guide. It's been published. It's what we all should reference back if there's any questions with a particular memory build. But really, your sweet spots are going to be 16 and 32 gig DIMMs, and then followed by 12 and 24 gig DIMMs. That's really the sweet spot for this. And again, all DIMMs must be the same. We don't support it's different memory from our earlier M5s. This is a new architecture, microarchitecture. So, the M6s use M6 memory. And again, the guide is published. So storage options, this is where we do have more options. And so you do have a front MES that supports up to 6 hot swappable drives. You do have M2 RAID module that actually doesn't exist on this, but sits between the CPU. And I've called out already, but there is no SD card support. If you need functionality that was provided by that, I would point you towards the M.2 if you need local storage. Boot from SAN is very popular, so I'll point that out as well. So you do have options on this front storage MES. You can go with a RAID card that's based off the Broadcom 3900. It's integrated into the MES. It does have built-in 4 gig cache that's not configurable. That's what comes with it. So you don't have to worry about configuring that. There is a pass-through module as well. And what we do is we pass through all the PCI Gen 4 lanes directly to all 6 NVMe drives on the front. So if you want NVMe options, you do want the X10C compute pass-through controller, and that really just extends the PCI to all 6, and it uses all lanes as well. And if you're using boot from SAN, you need no drives whatsoever. This would be the front bezel blanking card that would just go on the front. A little about the MES. The drives are hot swappable. You can mix and match. If you go with the RAID card, you can mix and match and use up to 4 NVMe drives, and I'll show you the configurations we support with that. With NVMe, there is no traditional RAID hardware. You'll have to use VROC for that. That is fully supported. And I did call out, and should call out, there is a SuperCap module on the RAID controller itself. So in addition to the built-in 4 gigabit cache, there is a SuperCap included as well. So protection for the RAID card if there is a power failure. This is the population if you've got a mix of NVMe and SAS or SATA drives. You can go with all SAS SATA. You can go with 1 NVMe, 2, 3, 4. If you need more than 4 NVMe drives, you have to go with the NVMe MES pass-through option to get all 6. So again, mix and match up to 4 NVMe with your traditional SAS SATA cards, where the SAS and SATA could use the RAID function. The NVMe still is not part of that RAID. If you need 6, it's the NVMe MES card itself. And again, just calling out based off the 3900 and SuperCap is included. And this is more detail around that. And then the pass-through controller, it does light up all 24 lanes at approximately 2 gig each. So you get full bandwidth of the PCI links all the way to the NVMe drives themselves. And it does not support SAS and SATA. Let's just call that out. And it is Intel VROC compatible with Intel drives. And this is the schematic of the M2 hardware. It does set between the 2 CPUs, as I mentioned. It can be a JBOD where you see both of them, or in an M1 RAID configuration. So a little on networking and data flow. This is really the guts of the system, or the plumbing. And you can see here, again, it's the 4th generation VIC. I've already mentioned it's based off the 1400 series, 256 virtual interfaces. That's been, we've had that for some time now. It is fiber channel and Ethernet virtual interfaces. So, I mean, this is what we've been familiar with. It does support VXLAN, NVGRE, and Geneva offload. You can see those here. And again, I'll call out those 2 interfaces are the physical links. The 2 interfaces you see at the top of the VIC are the 2 interfaces that we have into the fabric. So a little more detail on it. So you would have your first VIC in the system. If you do add a second VIC, you do have the bridge card that will be configured on top of it. So if you would have the MLOM, you would add the second VIC, and if you did that in the field, you would actually at that point install the bridge card on top of it. You can see it sets down into the little the pins, and it provides passive traces for connectivity. And what this does is it also offers as a conduit for traffic from the second VIC to get out the first VIX physical interfaces. In the event that MLOM fails, these passive traces will not be affected. You still have your physical traces lanes that will go out those physical interfaces that are on the MLOM. So that's how that works. That also allows us connectivity to that second VIC, has those physical interfaces that connect into the intelligent fabric of the X fabric as well. So again, that's not really talking about the X fabric in this session. That's really futures roadmap, but that's where the physical connections do come into the X fabric. A little eye chart to show you the different configurations. One with the 14425, which is the MLOM, and then the 14425 plus the 14825, which is the second. So with the one VIC, 100 gig, and that's 50 gig per IFM. That does require 2 VNICs. And because what we do actually have coming out of the physical interface is a 25 gig KR connection. So we do have 2 of those per VIC. So 2 times 25, you get 50 gig individual throughput to each IFM. So with 2 IFMs, you know, that's 100 gig. Each individual flow is 25 gig. So an individual flow, 25 gig, no matter, you know, how many VICs you have. But when you combine 2 VICs, you do double each one. So per IFM, you would be getting 100 gig with dual VICs to each IFM. So you end up with a total of 200 gig of throughput with 2 VICs. And that's 100 gig per IFM, spread across 4 by 25 gig KR links. So max flow 25 gig again, but to each IFM you get 50 gig, and remember you have 2 IFMs connectivity per VIC. So I know it can be a little bit confusing at first blush, but just remember that for each VIC connection, I have 2 connections into the IFM, and I have 2 physical connections out that VIC. So that's 2 times 25 times 2. So that's how the math works. And this probably depicts it much better. This is a 2 CPU setup. You have the 2 25 gig links coming out of the IFM A to Fabric A, 2 25 gig links coming out of the port group B to Fabric B. And that's how you know, you got 2 times 25 on each side, so that's 100 gig per node. Add in a second VIC and the bridge card, and we light up twice as many traces. Again, that's a passive link across the bridge and passive links through the 14425, the MLOM. And at this point, you've got 200 gig, 200 gig of total throughput from the node itself. And again, that's divided up into 25 gig individual flows for a total of 200 gig per node. And how does it show at the OS level or the hypervisor level? In today's B200M5, you'll show 2 20 gig links, and in the M6 with X-Series, the 210C, you're going to show 50 gig of throughput out of both. I've got some screenshots of this actually taking place. You can see that I'm showing 50 gig of aggregate throughput per VNIC and an individual flow of 25 gig. And we do the band, that's an aggregate of 50 gig per VNIC. So if you look back, if you go forward and you take 2 VNICs and you add the traffic between fabric A and fabric B, you can see you get a total of 100 gig of throughput in this scenario. This is a little bit more of an eye chart, but what we've done is we've added in the second VIC and connected it to fabric A and fabric B with 2 VNICs each. And at that, you get 200 gigabit of throughput through this node. And with that, we're going to segue to the power and cooling section of the agenda. And Jeff Metcalf is going to jump in and take us through this section of the presentation.
Hello, everyone. Again, my name is Jeff Metcalf. I'm a technical leader within the CTO organization, and one of the areas of focus that I support to the vertical is power and cooling. Hence, I'm helping Jeff cover this section for the partners in our UCS X platform. So what I'd like to start here with is there are a lot of eco-design standards that are being developed and are released. Here in the United States, Energy Star is the predominant one for servers that provide stringent thresholds regarding active efficiency. So this, you can think of this as like a miles per gallon requirement for cars applied to IT equipment. So it's basically performance per watt. A workload is run and executed, power consumption is measured, and it reports a performance per watt score. And the Energy Star specification basically sets specific limits on minimum allowable performance per watt scores. Then you have the EU regulation 2019-424 that took effect. This not only includes energy efficiency criteria, but it also extends to other environmental criteria, to enable circular economy. For example, maintaining access to firmware for EOL products so that they can be leveraged and reused and repackaged for other at the end of their useful life. So again, to enable the circular economy. Then we have EPEAT, which is very similar to the EU regulation regarding its span of not only energy efficiency, but other areas regarding, material usage, recyclability, circular economy, things like that. This was typically predominant for commercial products. It's been extended to enterprise servers. But what this shows is just the many certifications regarding, green initiatives, eco-design around servers. So Cisco UCS X-Series will be compliant with all of these, and the declarations will be publicly available on the Energy Star site or Cisco site, depending on the standard or the individual registry. Okay, next slide, please. Okay, so what I want to talk about here is some of the innovation regarding the thermal and power management features within X-Series. So in the previous generation chassis, the 5108, we collected temperature sensors only, and we didn't necessarily collect temperature sensors from all components. We did some correlations. And the reason being is the engine that we had for managing these temperature sensors wasn't sophisticated or capable of handling the multitude of sensor inputs, right? Also, the polling frequency was limited to 15 seconds. So what we've done is we've actually increased the polling frequency from 15 seconds to 5 seconds. And then also we've added this new feature. So we've added power consumption. So if you think about it, if you put like a saucepan or a pot on your stove and you turn your stove on, it takes some time for that pot to reach a certain temperature. Even though you've turned the gas or set the electric to a certain temperature, there's a delay. It's called hysteresis. Well, actually what we're doing now is we're actually looking at the power consumption of the processor. So we're going to extend this to other domains to basically manage the fan speed algorithm. So if we see a certain power consumption, we know the artifact of that is going to be increased temperature. So what we'll do is we can do some small incremental fan speed increases of like 1, 2, 3% to basically prevent the overshoot or overshoot. So basically, by the time that we react to these temperature changes, the temperatures hit a certain point that we have to do a much larger fan speed increase. So what this does is this allows us to right-size the response of the fans to thermal increases. So what this does is this reduces sound power, improves noise quality, and also reduces overall system power consumption, hence improving power efficiency. So one of the innovations there. Okay, next slide, please. So what I did here is I don't show all the components here, but what I do is this is just a top-down view of the compute node, and it just talks about all the sensors that are located on the compute node. And if you looked at the previous generation, the M5 blades, for example, we had the ability to collect local drive temperatures, but we didn't include them in the fan speed algorithm. This is a shift with the X-Series. We've actually, anything that has a temperature sensor, we are including in the fan speed algorithm. Previously you thought, okay, why didn't you do it before? Well, we're like, hey, the disk drives are located in front. They're receiving fresh air. Their operating temperature is 50 to 55 C. We set the limit for the blades as a 35 C inlet. So, hey, we don't probably necessarily need to keep track of those drives. Well, there are other instances where, it might be important to know what those drive temperatures are. So in your data center, a lights out environment, you may have some piece of cellophane or some type of packaging material from an adjacent install, right, that hits the floor and gets blown into your server. And all of a sudden you have two local storage devices that are reporting higher temperatures. So it's important to basically aggregate, collect that information, and also include it in the fan speed algorithm, right, to handle those things. So the takeaway here is we have a huge number of sensors in the system, and we're including all those sensors in the fan speed algorithm to include power consumption to basically right-size the fan speed response and optimize power consumption. Okay, next slide, please. Okay, so what I want to talk about here is kind of the environmental operating conditions, and then also kind of some other sensors. So within the chassis, we have kind of a pseudo chassis sensor. So basically, there's an intake sensor for all the nodes. Those sensors are muxed together, and then the lowest value is reported as the chassis value. Okay, it doesn't mean that you don't have access to the other sensors. They are just, if you were looking for the chassis only temperature, that's what it equates to. It's a pseudo sensor, so one of the inlet nodes temperatures. Then also we have some fan speed responses that we're starting the fan speed increases. So again, we were talking about temperatures and power, but there are other conditions that would cause a fan speed increase. Or, for example, a fan failure, for example, if you go from an N+1 to N condition, these fans would increase to a higher operating speed, 90% PWM. But what I wanted to talk about here as well is that on the previous generation of chassis, we only supported ASHRAE class A2. So that was an elevated temperature or max temperature of 35 C. There's 4 ASHRAE classes, if you're not familiar with their class: A1, A2, A3, and A4. A3 and A4 equate to higher operating temperatures or extended operating temperatures. If you're familiar with C-Series, we support that today. So we are currently in the certification effort of compliance certification for extended operating temperatures for the X-Series to support A3 and A4. What that's for is those data centers that want to take advantage of free cooling and reduce their overall power consumption from mechanical cooling. So they want to operate at temperatures at or above 35 C. That being said, there are obviously configuration limitations that come with that. There's caveats. There's no free lunch in this world. So when you do operate in those elevated or extended operating temperatures, there will be restrictions on the CPUs that are supported, the NVMe drives, memory, things like that. And that will be called out in the product specification sheet, once that capability is enabled. Okay, but initial launch, it's A2 35C, but again, we'll be extending it. Also, the current certification effort is going on for NEBS level 3. So any of those partners that are supporting customers that need carrier grade solutions, this product will be certified for NEBS level 3. The timeline for this is probably looking at the end of the the quarter calendar year, so at the end of this year to the first part of next year when that certification effort will be completed. Okay, next slide. Okay. Another area of innovation with the X-Series is on the 5108, we had a common plenum And if one sensor within the chassis required additional cooling, all the fans increased lockstep, the same speed. What we've done is we've changed that approach and we've gone to a zone-based cooling. So if you look at this, we have basically vertical and horizontal partitions, and there are sensors that are contained with each one of those partitions, and there are fans that support those volumes or those zones. And so what happens is when you have a component in that zone that was requesting for incremental cooling, just those fans respond to that so that you don't drive all the fans. So this reduces overall fan power, and it also improves sound quality in the solution. So this is another area of innovation, zone-based cooling with the X-Series chassis. Next slide, please. Okay. So what I want to talk about here, I think Jeff covered this earlier, but I just wanted to go back and talk about the fans. So we basically have 4 system fans. These are 100 millimeter fans. The reason for selecting 100 millimeter fans above the 80 millimeter fans that you see in the current 5108 is these larger fans, we can operate them at lower fan speeds and move the same or more air volume. But by operating at lower fan speeds, we can reduce power. And those are you familiar with fan affinity laws? I'm certain there's not many, but power consumption is not directly proportional to fan speed. It's actually a cube rate. So when you increase the fan speed, it's a cube of that proportional response, right? So for example, these fans at idle can be consuming 3 watts, for example, but if you move it to 50%, just a 50% increase, it's not a 3 watt increase in power, right? The fans increase to almost 60 watts each, right? So it's a cube rate of that response, right? So the objective here is to try and run the fans as slow as possible. Hence the reason we selected these larger fans. Okay. Also, the IFMs, the blanks, and the future FEM modules have fans as well. They're N+1, just like the system fans. There's 3 fan modules there. I believe Jeff showed an earlier top-down view of the IFM that showed those fans, and they're hot swappable as well. Okay. So just the takeaway from here is just the sheer amount of airflow. So again, this chassis is designed for 10 years and beyond. So we've over-provisioned the volumetric airflow capability of the system fans to support air cooling into the future, with 1,000 CFM. So by no means at first launch are we going to require 1,000 CFM to cool any type of solution, based on Ice Lake. Again, this is built for 10 years. You can think of the frame or the chassis, is kind of like the infrastructure when you're building a city, right? You're laying roads, sewer lines, electrical power lines, right, for the population that you think will be in the future. You obviously won't be using that today. So what we've done is we took a page out of the 5108 playbook, right, and we over-provisioned everything, right, because we don't know what technologies will evolve and lead in the future, and we wanted to give as many degrees of freedom to our customers going forward. So we over-provisioned everywhere we could. Okay, next slide, please. Okay, so this is kind of a comparison of the airflow where we talked about that. So if I just oriented you to this chart, on the horizontal axis is fan speed. It goes from 10% to 100% PWM. So you can think of this as 10% speed to 100% speed. On the vertical axis, you have volumetric airflow, or the volume of air that's going through the system. Okay. On the bottom, you have a blue line that represents the airflow as you're increasing the system fan. So you basically see, at the lowest operating point around 20%, the system's basically delivering about 160 CFM. And if the fans are running all at 100%, you're delivering just around 600 CFM. Okay. And what I show kind of some intercepts on that line, an M4 and M5 blade, kind of the typical operating points. So the fans are kind of operating around 30% or 50% fan speed when those blade versions are installed. Okay. So looking at the other 2 curves, so you have an orange curve and a gray curve. And again, there's multiple fans in here. They have independent operating, so it's kind of hard to show this looks more like a, calculus. It would look more like an integral, right? The area under a curve of what these fan speeds would look like. But what this is, it just kind of shows the range. So the top one is we've increased the system fans from 20% to 100% and set the FEM and IFM fans to 100%. So that's the max, right? So you basically see the airflow capability, gets well above 1,000 CFM, around 90%. Okay, and then the orange curve, we set the IFM and FEM fans at 20%, right, and increase the system fan speeds, and you kind of see where you're at on those areas. What I wanted to point out here is, again, we have 1.7 percent or 7 times more cooling capacity, more airflow that we can move through the X-Series chassis compared to the 5108. Again, to account for these next generations of technologies, right? Higher power CPUs, FPGAs, and other accelerators and high-speed fabrics. Okay, next slide. Okay, so this is kind of another example, just a different way of looking at it. So you have the orange curve, which is kind of the cooling capacity of the X-Series chassis. The blue curve is the cooling capacity of the existing 5108. And what you have on the horizontal axis is chassis fan power, so amount of power that the system fans are drawing. And on the vertical axis, you have how much power is being removed from the system. So every watt of electrical power that goes into the chassis, or any server for that matter, is removed as heat energy. So for every watt of electrical energy, it's basically removed as heat energy. So if we had a like solution, the solution was consuming 4,000 watts or 4 kilowatts, you basically draw a horizontal line to see where the intercept will be on that curve. And on the orange curve, what you see is there's about 170, 180, watts of power required by the system fans for the X-Series chassis. And on the B-Series chassis, the 5108, it's more like around 230, 240 watts, basically a 30% reduction in fan power required to cool the same thermal load in the chassis. So again, that's just a takeaway of all those things that I talked about earlier. Larger fans spinning at lower speeds, you're drawing the same amount of air volume, through the system. Okay, next slide. Okay. So what I want to talk about too here is kind of the policies. So this is a kind of a snapshot of Intersight and some of the things that we've done on the thermal side. So if you're familiar with the C-Series today in standalone mode, there's a feature called dynamic inlet temperature threshold. And what this is the C-Series can support those classes that I talked about earlier, ASHRAE A2, A3, and A4. They have different upper limits. So what we do is we allow the user to go in and select the upper limit for that threshold. This is being extended to Intersight and will apply to Washington, the 9508 program as well. So it'll basically be a policy that's applied to a server or a chassis, right? So it's agnostic whether it's a server or a chassis. And again, what this is if you're familiar with UCSM threshold policy, it's kind of very similar to that, a user-defined threshold. Okay, next slide, please. Okay. Another one is fan control policies. So this is another innovation with Intersight and X-Series. So basically, we're extending kind of the policy framework for fan policies. Again, these are non-disruptive changes. They don't require, any reboot, unlike other solutions that embed fan speed policies in BIOS settings. These are abstracted out of BIOS and can be applied non-disruptive. That way, they can be based on time of day or reaction and things like that without requiring any type of downtime. But what it is here, if you're familiar with a UCSM, this policy was global and applied to all the endpoints managed within that UCSM domain. And then on C-Series, you had all those policies, but they only applied to those C-Series. And again, you could use those policies within UCSM and extend them to C-Series, and it worked fine. It was only global for the Blade products, right? So what we've done now is we've extended that policy, and that policy applies the state only to the endpoint that it's applied to. So you can have multiple endpoints or managed objects within the domain that have different fan speed policy requirements. So you may have a dev environment, a production environment that have different environments. Also, you can have policies that react and basically change the fan speed based on, the workload that's being done, right? So for example, you could transition from an acoustic low power, one that's biased towards energy efficiency, more towards maximum, or a more aggressive policy, right, to ensure that there's no impacts of throttling based on thermal events or something like that. Or it could be in reaction to, hey, you want to take advantage of some free cooling hours. So what you want to do is you want to bias this policy from energy efficiency more towards active cooling, so a higher power or a higher performance policy and stuff like that. So the key takeaway here is we've extended all these policies, acoustic to max power. And again, it's no longer a global policy. It's an individual, it only applies to the managed object that it's applied to. Okay, next slide, please. Okay, so I want to kind of wrap up the thermal piece here, talking about liquid cooling. Jeff showed some of this early on, but what I want to do here is kind of set the stage of workloads that are kind of driving liquid cooling. So this is basically have a set of workloads on the horizontal axis and kind of a percentage of customers today in the industry that are applying or using these types of workloads. So you kind of see three that kind of step out to you. One is high performance analytics, low latency processing, and machine learning. So high performance analytics, the things that are driving that are, graph type data sets, very large data sets. The other one is, doing analytics on streaming data. And the components that are kind of driving the need for liquid cooling in this area would be accelerators and CPUs. On low latency processing, again, this is kind of like high frequency trading, and the components, the hardware components that would be driving liquid cooling on this would be the frequency optimized processor SKUs that have higher TDPs, and then also accelerators, right, FPGA type things that are driving those. And then lastly, machine learning and artificial intelligence. The predominant driver here is GPUs, obviously. So basically a lot of the traditional graphics workloads, basically pixel shading or ray tracing, are very good for machine learning, artificial intelligence, doing very large multiple matrix multiplication, while maintaining high floating point operations and stuff like that, are really good for GPUs. So the three type of hardware elements that are driving liquid cooling are CPUs, certain bins of CPUs, GPUs, and certain bins of accelerators. So next slide. So Jeff showed a similar slide to this. This is kind of like a time horizon on when we might see liquid being more predominant in the data center today. So there are CPUs and GPUs and accelerators today that are designed for liquid cooling, and they're predominantly for targeted large scale customers. They're not generally for general consumption. And kind of what I show here, again, I have on the horizontal axis kind of a timeline from 2020 to 2024. And then on the vertical, I have an icon for CPUs, icon for GPU, and that rocket ship is accelerators. And then what I show there is kind of the top end power or TDP for that type of hardware component. Like for example, in 2020, we have 205 watts for the CPU, 300 watts for GPU, and 100 watts for the accelerator. So where things start getting interesting is kind of in the 2023 timeframe. So kind of towards the, I would say the M7, beginning of the M8 type timeframe. You're going to start seeing CPUs that are going to be available for general consumption that are targeted for specific workloads that would require liquid cooling to maintain specific junction or case temperatures. And then maybe a little before that, you're seeing some GPUs coming into that timeframe. And what we're seeing with the GPU vendors is typically the GPUs provided a turnkey solution that included a thermal management solution. And you have kind of the MXM form factor, right, that you see kind of in blade form factors where the GPU vendors, remove the thermal solution and kind of turn it over to the OEMs to develop their own solution. We're kind of seeing that transition as well in the PCI form factor. So for example, OEMs are going to the GPU vendors and saying, hey, we want to use the GPU, but we want to orient this standard PCI full height, half height GPU in a different way to package it differently for our types of solutions. So what you'll see is you'll see GPUs that will be providing OEM specific thermal solutions. these will be solutions that will be air-cooled and potentially liquid-cooled. So the takeaway here is just to reiterate what Jeff had discussed, that it doesn't mean that everyone will require liquid cooling. Okay, it means that there are certain hardware components that will be enabled for liquid cooling to take advantage of certain workloads or certain attributes that those pieces of technology will be available. So again, with this, when you think of a CPU, there's many SKUs of CPUs. There may be, 3 dozen CPU SKUs that will be offered, and there'll be 1 to 2 that will be optimized for liquid cooling. The remaining balance will be air cooled. You'll see something similar with GPUs and something similar with FPGA. So the takeaway here is, it doesn't mean you have to. What it means is it's being enabled. Okay, next slide. Okay, and what I want to talk about is the solutions that we have here, right? So, the approach that Cisco took with this architecture is to try and take a page, out of the software playbook, right? And make things as restful as possible, right? And define kind of API references, right? And develop methods or microservices that can be consumed. You can think of liquid cooling as a microservice, for example, that can be consumed or not consumed depending on your need. Okay, and there are 2 approaches that Cisco is looking at. So there's an open solution and a closed solution. Okay, a closed solution would be all the componentry, all the components required to provide liquid cooling would be contained within the chassis. So this would be an easy uptake or easy deployment for a customer that may have an existing brownfield environment that hasn't, plumbed for liquid, way to basically move, that heat from liquid form into another liquid form and reject it some way, right? So there may not be, their data center may not be provisioned to support liquid cooling. They may not have liquid lines in their data center. They may not have liquid lines going to their white space. They may not have the ability to add, CDUs or heat exchangers within their rack and stuff like that. So on the left side, you see a closed loop solution. So what we would do is we would use the volume that's currently allocated for the FEM or X fabric. And here you would install basically a self-contained unit that basically has the heat rejection. So basically the liquid loop is in there. You have direct connects, a blind mate dripless connectors. So basically the compute node or accelerator node would plug in from the front, and it would mate to a set of liquid lines extending inside the chassis, much like the IFM's, the IO connection is made with the nodes today. But these liquid lines, and everything would be contained in there. So the downside with this option would be it's consuming the volume that could be used for the secondary fabric. And this could be a PCI fabric, this could be some future high-speed fabric. So if it's a PCI fabric, what that means is, okay, if we're using PCI fabric to extend a GPU node, as a pool of GPU resources that can be connected to compute nodes based on intersite policies. Well, if you remove that capability, then you don't have the ability to extend those GPUs to that. So that's the trade-off. So this would be limited for solutions that are wanting to do liquid cooling for CPU and memory. So in the memory, there would be a manifold that would extend around the DIMM area, and then a cold plate on the CPUs. Okay. On the right-hand side, we have an open loop solution. So on this solution, I picture a compute node, but it doesn't mean that it couldn't be a GPU node, for example, or an accelerator node. But in the GPU node, what would happen is we'd have cold plates and manifold connected to the CPU and memory complexes. Those liquid lines would egress out to the center of the node. The downside to this is that you have to give up 2 local storage bays to provide the volume for liquid lines to egress. And then from there, it would be a dripless universal quick disconnect. It's the same universal quick disconnect that's being developed within the Advanced Cooling Solutions Working Groups for OCP, Open Compute Project. So leveraging that same design. And then from there, the liquid rejection can be many different ways. What I show here is kind of a block for a Cisco branded CDU. This would be a 2 to 3U liquid to liquid heat exchanger, but it doesn't mean that you can extend it to anything. You could, plumb it directly to a 0U manifold. You could plumb it to a heat exchanger. So there's a lot of flexibility from that point on, basically moving the liquid to those other solutions, right? So those are the options there. The other thing that I wanted to talk about here is on the X-Series. So when you think of liquid cooling, there's kind of two types of liquid cooling. You hear the term immersion cooling and direct attach. So immersion cooling is exactly what you're saying. You're immersing this IT equipment in a bath of non-electric, non-conductive fluid like mineral oil. And there's 1 and 2 phase versions. We're not targeting this solution for liquid cooling. There's several reasons: serviceability. So, for example, when you install this into the bath, right, and you have to do type of service, we have servicing from the front and rear. So basically, you'd have to invert this chassis on the side. So there's a lot of trade-offs with doing immersion cooling for this type of architecture. Immersion cooling would be something more conducive to a rack product, stuff like that. So the takeaway here is we are provisioning for liquid cooling. We have two options: a direct and an open and a closed loop solution. We'll be offering both, and it's direct attach, not immersion cooling at this point. Okay, next slide. Okay, so now I want to transition into power. So at initial launch, we'll be releasing a titanium-rated power supply that supports high line and low line. The output capacity at high line, that's 200 to 240 volt AC, is 2.8 kilowatts or 2,800 watts. At low line, 100 to 120, it's 1,400 watts. The reason being is power is a multiple of current and voltage. If you reduce the voltage, then hence you reduce the output, right, of the power supply. Post FCS, we'll be introducing a 48 volt DC power supply and a universal power supply. So the universal power supply will support high voltage DC and high voltage AC, and most likely high line AC as well. That's 200 to 240. However, it will not be rated at titanium. It will be a platinum rated power supply. Okay. And if you're familiar with the 5108 today, on the right-hand side, we have kind of a power entry module. You see, 3 input connectors on the top and 3 input connectors on the bottom. This is a power entry module. So what you're seeing there is kind of the IEC, 60 to 30 C20 inlet. If you did a -48, you'd have a set of terminal lugs. If it's a universal, we'll be using a safety grid input connector. But on the 5108, we also support 48 volt DC, high voltage DC, and AC input. However, you had to make that choice up front, and once you made that choice, that chassis was branded as that, and it could not be swapped out. It was a chassis swap. What we've done is we've changed that power entry module to be a FRU. So if a colo, this equipment moves colo facilities and the power delivery is different, you have the ability to change the FRU module, change the power supplies, for example, in the field. You don't have to do a complete chassis swap. Or, if there's an acquisition and equipment comes into a company's data center from an acquisition, that was maybe provisioned for a different type of input, can easily swap these out to maintain, the ROI, right? Extend the life of this chassis, okay? We'll support N+1, and then N+2 is a new capability, and N+N or grid power redundancy policies. The chassis has been tested well above 14 kilowatts as far as distributing power. So in the future, we may release a power supply that's rated above 2.8 kilowatts, for example, in the next 10 plus years at some point. But right now, we're stating that the chassis power delivery is supporting 14.4 kilowatts going forward. Okay, next slide. Okay, so this is kind of an example or the InterSite policy. This is a workflow defining a power policy for a chassis or a server. It's very similar, right? We've basically abstracted that, and you can apply these same policy settings to a standalone chassis or a modular chassis like the 9508. I'm not going to go through all the policy selections here, but you can kind of see them. I'm just going to talk about some of the highlight some of them. So we have redundancy policy. Those are available today within UCSM and also standalone. The ones in UCSM today are N+1, and grid, or N+N. Or as I said earlier, we'll be extending N+2 to the 9508 chassis. But what's different here, just like the fan speed, the policies are no longer global policies. So within UCSM, all UCSM managed endpoints had the same policy, whether it was a C series or a B series. Going forward, the policies will apply state only to that profile that they're applied to, chassis or server. So you can have multiple power redundancy policies within the same logical domain. So it doesn't matter. So again, you could have a dev environment that has a different policy compared to a production environment that may have HA requirements, right? Next slide. Okay, so this is rebalancing. So today we have rebalancing. So what this concept is within the chassis, you have a certain amount of available power. Not all workers consume their full power allocation, simultaneously. So what we're trying to do is minimize stranded capacity with static loads. So what happens is each endpoint is given an initial budget. If that endpoint, that node is consuming 90% or more of its allocated budget, it makes a request to increase its budget. The chassis management controller looks across all the endpoints. If there's an endpoint that's consuming less than 75% of its budget, it basically redistributes that power allocation to that high consumer from the low consumer. Okay, so what this is just a stewardship using all the available power, not having stranded capacity. So this was a policy that was enabled and always on by default within UCSM. But what we've done is we've taken a different approach. We don't know all the ways that a customer may want to implement it. So what we're doing is we're exposing all these policies as users. We're assigning the default that we think is most appropriate for the vast majority of our customers, but we're extending the capability for customers to enable a policy that may work better for their situation. So the default is enabled, but by all means, the customer can disable this policy. And what happens is there would be static power budgets assigned. Those initial budgets would be static and go forward. Okay. And again, these policies can be changed. They're non-disruptive, right? They're not embedded in BIOS, don't require a reboot or anything like that. Okay. The next one that I want to highlight is extended. Can you go back one slide, please? Yeah, so the next one I want to highlight is extended capacity. So this is for environments that are operating in grid. So if you have 6 power supplies, and the reason we did 6 power supplies is we're seeing as we're getting to these higher density components, customers are bringing 3-phase power to their rack products. So they have basically 3-phase rack PDUs. And what the PDU does is it strips off 1 phase and provides single phase to each power supply. So the power supplies are single phase. So what happens though is to balance the load across each one of those phases, you need to have multiples of 3. Hence we move from 4 power supplies to 6 power supplies to improve load balancing. So in grid mode, where you have 6 power or kilowatts of available power. But we're seeing in the future that, hey, we may want to be able to extend the capability of doing that. And what we're doing is we have the ability with some features within the power supply and our ability to react is we can provide an effective capacity of the power supply and extend that power supply from 2.8 kilowatts to 3.2 kilowatts. So extending the available power in grid mode from 8.4 kilowatts to 9.6 kilowatts. Okay, this policy is disabled by default. Customers can enable it. This will be a post FCS feature. Okay, next slide. Okay, so we also have power restore. Again, I'm not covering all these features, but this is very similar to restore last state. So during a planned or unplanned an outage, you can decide what state you want this endpoint to return to. Return to its last state, always off or always on. So you can do this in standalone today or within UCSM within the service profile. This is being extended to the server profiles within InterSight to enable this feature. because for example, there may be a node that you want to control to come up first, right? To trigger, other nodes coming up first. So this is a way to have a controlled recovery, right, from a planned or unplanned outage. Okay, next slide. Okay, the next area I want to talk about is power budgets. So within UCSM, it's called power groups. Within C-Series, power capping. But basically what we're doing is we're extending the ability for the user to assign explicit power groups or power budgets to endpoints, right? So what happens is within Intersight, you'd make a query, to what endpoints you want to add to a specific group. That query would basically do a GET request, right, to understand what are the min and max range of that power. Hey, here are the power values. And you can set a specific explicit budget, and then based on the power allocation priorities, that power will be distributed amongst those endpoints. This is kind of an example where we're extending a lot of the policy features that you see in C-Series to this Intersight policy so that you can do, explicit power budgets based on certain triggers, right? So it could be based on a time of day, or it could be based on, a trap, an SMP trap, or, something from a syslog server trap, any other trap, right, to basically drive this response. So this is an example of setting a power group for one endpoint and assigning, hey, the min and max range, what's enforceable and stuff like that. Okay, but it's very similar if you're familiar with the C-Series, basically extending that same look and feel to Intersight, and again, it'll be applied across the entire X-Series domain. Okay, next slide. Okay. The last piece I want to talk about is the UCS Power Calculator. So this is our tool for sizing workloads. This X-Series is available today. The URL is simple. You can just search with any browser you choose. Just look UCS Power Calculator. It should be the first hit that comes up, or it's ucspowercalc.cisco.com, and this is just an example of the a summary of the power calculator, right? That provides information regarding weight, airflow, and things like that current. Okay. So with that, that wraps up my section, and I'll turn it back over to Jeff to close this out.
Well, thank you everyone for joining our call or our session this morning. And please use the team space for any Q&A. I did see a lot going through there. And now I'll turn it back over to Rick.
Appreciate that. Hey, there was one question that I got pinged. It wasn't in the room. It was just someone pinged me on the side. Maybe we could address it live. And that is around the behavior of traffic going from one node to another node through the IFM or up through the fabric. Can you talk a little bit about that?
It follows the same rules that we had in the previous 5108 with IOMs. Obviously, if they're in a different layer or subnet VLAN, that traffic goes up to a third-party a Nexus switch, preferably, and makes that boundary change. If it's in the same subnet, it could get switched within the fabric to the other node.
Okay, but not at the IFM.
No, it'll go up to the fabric interconnects.
Okay, great. Thank you for clearing that up. We really appreciate the session today. Thank you, everyone. We're now going to be taking a break until 1 p.m. Eastern. So we'll be back in about 25 minutes. We'll see you all then.